Polynomial time as a definition of efficiency. When people first began analyzing discrete algorithms mathematically, a thread of research that began gathering momentum through the 1960s, a consensus began to emerge on how to quantify the notion of a reasonable running time. Search spaces for natural combinatorial problems tend to grow exponentially in the size n of the input if the input size increases by 1. The number of possibilities increases multiplicatively. But like a good algorithm for such a problem to have a better scaling property, when the input size increases by a constant factor, say a factor of 2, the algorithm should only slow down by some constant factor c. Arithmetically, we can formulate this scaling behavior as follows. Suppose an algorithm has the following property. There are absolute constants c greater than 0 and d greater than 0 so that on every input instance of size n, its running time is bounded by c times n to the d primitive computational steps. In other words, its running time is at most proportional to n to the d. For now, we will remain deliberately vague on what we mean by the notion of a primitive computational step, but it can be easily formalized in a model where each step corresponds to a single assembly language instruction on a standard processor, or one line of a standard programming language such as C or Java. In any case, if this running time bound holds for some C and D, then we say that the algorithm has a polynomial running time, or that it is a polynomial time algorithm. Note that any polynomial time bound has the scaling property we're looking for. If the input size increases from n to 2n, the bound on the running time increases from c times n to the d to c times 2n to the d, which is equals to c times 2 to the d times n to the d, which is a slowdown by a factor of 2 to the d. Since d is a constant, so is 2 to the d. Of course, one might expect it. Lower degree polynomials exhibit better scaling behavior than higher degree polynomials. From this notion and the intuition expressed above emerges our third attempt at a working definition of efficiency. Propose the definition of efficiency 3. An algorithm is efficient if it has a polynomial running time. Where our previous definition seemed overly vague, this one seems much too prescriptive. Wouldn't an algorithm with running time proportional to n to the 100, and hence polynomial, be hopelessly inefficient? Wouldn't we be relatively pleased with a non-polynomial running time of n to the 1 plus 0.2 times log n? The answers are, of course, yes and yes. And indeed, however much one may try to abstractly motivate the definition of efficiency in terms of polynomial time, a primary justification for it is this. It really works. Problems for which polynomial time algorithms exist almost invariably turn out to have algorithms with running times proportional to very moderately growing polynomials like n log n squared, or n cubed. Conversely, problems for which no polynomial time algorithm is known tend to be very difficult in practice. There are certainly exceptions to this principle in both directions. There are cases, for example, in which an algorithm with the exponential worst-case behavior generally runs well on the kinds of instances that arise in practice. And there are also cases where the best polynomial time algorithm for a problem is completely impractical due to large constants or a high exponent on the polynomial abound. All this serves to reinforce the point that our emphasis on worst-case polynomial time bounds is only an abstraction of practical situations, but overwhelmingly, the concrete mathematical definition of polynomial time has turned out to correspond surprisingly well in practice to what we observe about the efficiency of algorithms and the tractability of problems in real life. One further reason why the mathematical formalism and the empirical evidence seem to line up well in the case of polynomial time solvability is that the gulf between the growth rates of polynomial and exponential functions is enormous. Suppose, for example, that we have a processor that executes 1,000,000 high-level instructions per second, and we have algorithms with a running time bounds of n log n squared, n cubed, 1.5 to the n, 2 to the n, and n factorial. In the table, we show the running times of these algorithms in seconds, minutes, days, or years for inputs of size n equals to 10, 30, 50, 100, 1,000, 10,000, 100,000, and 1,000,000. There is a final fundamental benefit to making our definition of efficiency so specific. It becomes negatable. It becomes possible to express the notion that there is no efficient algorithm for a particular problem. In a sense, being able to do this is a prerequisite for turning our study of algorithms into good science, for it allows us to ask about the existence or non-existence of efficient algorithms as a well-defined question. In contrast, both of our previous definitions were completely subjective and hence limited the extent to which we would discuss certain issues in concrete terms. In particular, the first of our definitions, which was tied to the specific implementation of an algorithm, turned efficiency into a moving target. As processor speeds increase, more and more algorithms fall under this notion of efficiency. Our definition in terms of polynomial time is much more an absolute notion. It is closely connected with the idea that each problem has an intrinsic level of computational tractability. Some admit efficient solutions and others do not.